We are now able to extend our understanding of circuits using KVL and KCL to our previous discussion of complex impedance. We're going to look at two different configurations of circuit components that form the foundation for finding total impedance. These are series and parallel configurations. It is useful to us to find the total impedance through a number of elements, because this dramatically reduces the complexity of analysis. So, how do we do this for series impedances? That is, a series connection of circuit components possessing some impedances Z. We know from Kirchhoff's current law that the same current will run through each of these components. That means that if we rearrange our equation for the total voltage drop, we find that we can group all of these impedances together in a straightforward summation. If we divide through by current I then, we are left with just the impedance relationship. Therefore, the total impedance of a set of circuit components placed in series is simply the sum of their respective impedances. In the case of a resistor, inductor, and capacitor in series, the total impedance is therefore ZR plus ZL plus ZC. What about for a parallel configuration of circuit components? Well, similarly, we know from Kirchhoff's voltage law that the voltage about either of those two loops will equal zero. Therefore, the voltage across each component must be identical. This means that if we rearrange our equation for total current flow through this network, that is, the total voltage divided by the total impedance, we find that we can group all these impedances together in an inverse summation. If we divide through by voltage V then, we are left with just the impedance relationship. Therefore, the total impedance of a set of circuit components placed in parallel is the inverse of the total sum of their inverse impedances. So for the same three components connected in parallel, the total impedance is therefore 1 on ZR plus 1 on ZL plus 1 on ZC, all inverted.